Hello, this is physical geology, and today we're going to talk about metamorphic rocks. Metamorphic rocks. Remember the rock cycle? We talked about igneous, sedimentary, and metamorphic. What was the keyword to the metamorphic rocks? Igneous, sedimentary, metamorphic. Remember the keyword for the igneous with the arrow had to be the melting. I put an M. And if sedimentary rocks melt, they become igneous. For igneous to become sedimentary, you have to have the weathering. So I put W, weathering. The metamorphic to igneous to metamorphic. Remember the keyword is heat and pressure. And from metamorphic to sedimentary, you got to have weathering, so the W. And from sedimentary to metamorphic, you need to have heat and pressure. Remember, that is the keyword for the metamorphic rocks, heat and pressure. Pressure and heat. So, what is metamorphism? The interesting thing about metamorphic rocks is that every change happened either with water, or it was crystallized. The rock was forming by molten rock crystallizing slowly as the temperature cooled down. What happens when there is a metamorphism, that it happens in solid state, means the crystals are recrystallizing, rearranging, like lattice by lattice, basically in solid state. So it's not going to be liquid, it's not going to be melt, it's going to stay in solid states, and it just recrystallizing lattice by lattice. And it happens because of the high pressure and temperature. And the new rock, what we call metamorphic rock, in nearly all cases will have different texture and very different mineral composition from the original rock, which is what we call parent rock. However, one interesting thing is that the original rock chemical composition and the new rock chemical composition has to be exact. So when you have a metamorphic process, basically you have to be able to write chemical equations for every changes, and it has to be balanced chemical equations. So whatever the element is in the parent rock is we're gonna have to be able to count for in the new type of metamorphic rocks. So the major concepts with metamorphic rocks is that it can form from any rocks. It could be sedimentary, igneous, or metamorphic, actually, to become a new metamorphic rocks. And it does involve recrystallization, and it happens in solid state, and it will have very low or no chemical change at all. You could have some low chemical change when you have CO2 or H2O coming out, but you have to be able to account for that, even that. Like you just have to be able to tell what happened with every kind of chemical component during the process. And the new minerals will form a new texture. So these are important things. And this picture just shows you an original igneous rock, granite, and the metamorphosed version of it, which is what we call gneiss. See, it has different texture, most of all. It does have, in this case, actually, it has similar composition, similar mineral composition. So what causes metamorphism? How do we find high pressure and temperature forming? In what kind of environment? First of all, you can have burial of sedimentary rocks. You know how sedimentary rocks settle down, accumulate in the ocean, and then they're gonna get covered by more and more and more and more and more sedimentary rocks. And just by going down big burial depth, we talked about the geothermic gradient, so we know as the temperature increases as we go down, then of course the pressure is increasing too. So that is one way to produce metamorphic conditions. And the other possibility is when you have plate tectonics. Like, just imagine an oceanic plate going under against the other oceanic or a continental plate. You know, I always showed it very simple, but to tell you the truth, as this happens, this area will actually form a lot of metamorphic rocks because of the high pressure and temperature right there, especially the pressure. So the two situation is when you have burial during sedimentary deposition, high burial depth, which increases temperature and pressure, or when you have plate tectonics, plate motion against each other, in case of oceanic continent and continent plate boundaries. So the principal agents of the metamorphism are the temperature, the pressure, and the chemistry of the original or parent rock, because as we know, that defines the chemistry of the metamorphic rock. So let's talk about the temperature changes. We do say that the mineral is stable if we give enough time and it still does not react to become a new mineral. Most likely the most stable minerals are quartz. That's very hard for it to form into anything else. So we could say that on surface condition, which is STP, standard temperature and pressure, that is 1 atmosphere and 25 degrees Celsius. So at standard pressure and temperature, quartz and clay minerals are the most stable. Quartz, I just put Q, and C for the clay. I say clay. Quartz and clay minerals are the most stable. You can give millions of years, it still won't change into anything else until the pressure and temperature environment changes. If you think about actually, the temperature probably is the most important factor in the metamorphic process, because the temperature, as it increases, the original minerals are becoming unstable and they will actually change into something else. But not only that, the temperature also changes the rate of reaction, because the higher the temperature, the higher the reaction rate. I have a story for you here. Like if you, let's say, have a first date and you buy a chicken because you were gonna cook it on salt, like I told you. I used to have a friend from Israel, and they were cooking on salt. When I say cooking on salt, they bought the ice cream salt, you know, those salts which has the big grains in it, really big grains. You can buy it at Walmart or Kroger, a bag for like $2 something. And then you get a pan, fill it up with 1 inch of salt, and you take the chicken, you know, the chicken you can buy at Kroger. Make sure that you pull out from the belly, you know, there used to be the neck and liver and stuff. So you pull that out and you replace it with an onion. Of course, peel the onion before. You put the onion in the chicken's belly, and then you put the chicken on the salt. Don't have to cover it, don't have to season it, you don't have to do anything. You put it in the oven on 350 degrees Fahrenheit for 2 hours. It's going to be the best chicken of your life. It's going to be perfect, moist, will have no fat because the salt pulls the fat out. And it put just enough salt so it will taste amazing. I also do ribs on the salt. The ribs are very good too. You don't have to put anything on it, but you have to cook it a little bit longer, like 2.5 hours, on like 380, 400 degrees. And the ribs are gonna just fall off of the bones. It's amazing. So anyhow, just try it. It's really good. So let's say on that day when you have a date coming to your house for the first time and you promise that you're gonna cook really good food, and you decide to go with my chicken or rib, whichever. But everything comes, you know how time is going when you have an exciting date or something comes up. So by the time you get home and you have to do all the makeups and getting ready, time is running out. So what are you going to do with your chicken? Because you realize, oh my God, I haven't put the chicken and it needs 2.5 hours. So what do? Yeah, you raise the temperature, because as soon as you raise the temperature, you know, the chicken is gonna cook faster. So then the date arrives and you start smooching and everything. And the last thing you will remember is what? Of course, the chicken. So suddenly your beep, beep, beep goes off and you smell, and you know, oh, the chicken. You know, when you raise the temperature, it increased the reaction rate, so the chicken cook much, much, much faster. And you know, it's not gonna get to good results. So you have to remember, the higher the temperature, the faster the reaction rate. So that's why the temperature has two functions. One is that it makes the original minerals unstable and they have to recrystallize to a more stable form. And on the other hand, the higher the temperature, the higher the reaction rate. So also, if you decide to pull down the temperature on that chicken, how long will it take for it to cook? Yeah, you're right, forever. So this is important to understand, that when the temperature is less than 200 degrees Celsius, the reaction rate is really going down. So it will take a long, long, long time for that chicken to cook. And it's the same with rocks. When you are in the sedimentary environment, like, you know, the STP, which is 1 atmosphere and 25 degrees Celsius, the reaction rate is so slow that rocks are able to stay around for millions of years without any change, 25 degree. And we call those guys metastable. So when we say a rock is metastable, that means that this rock is more stable when the temperature is high, like igneous rocks. You know, they finish crystallizing around 800 degrees Celsius. That's where they are stable. When you put them down to 1 atmosphere and 25 degree, they're not really stable, but because of the reaction rate is so slow, they will stay around for a long time. We call them metastable. Just remember that, metastable. When you have the temperature which is really, really high, almost at melting, we see that the minerals, the rocks, don't know if they should melt or recrystallize. So you will see rocks which have one layer of recrystallized minerals and one layer of molten, you know, minerals which are coming out of magma. And we call that migmatite. That's when the rock cannot decide if they should metamorphose or become igneous rocks. So we call the rock formed in extreme condition like this, migmatite. Okay, the second very important thing is the pressure. And we have two kinds of pressure. One is the confining. Confining or hydrostatic means that the pressure is coming from every direction. You have to imagine yourself as scuba diving. When you go underwater, the pressure is higher, but this pressure is acting on you exactly the same way at any place over your body. So that's what we call hydrostatic. And when you have hydrostatic pressure, basically the pressure acting on the mineral makes it actually more dense. Like, this is had difference between graphite and diamond forms. Remember, we saw that the diamond has a much more dense structure versus the graphite, where you have those sheets, but in between the sheets there is a lot of roots. The sheets are far away from each other. So you have, when the high pressure is hydrostatic, you're gonna have this very, very close atomic packing. The other type of pressure is the so-called directed pressure. Directed pressure is when the pressure is coming from one direction. And basically what it does, it makes the rocks to have this flattened structure, which is the reaction to the directed pressure. And we call that foliation. This is the result of the dynamic pressure. So this is how the so-called foliation forms, actually. And this slide is about the chemical activity during metamorphism. I already mentioned it to you that some minerals, like we have amphibole, biotite, um, when they actually recrystallize in high pressure temperature environments, usually the amphibole or the biotite is not going to stay stable because it has like built-in water in their structure. So when they recrystallize, they will become minerals which don't have that, like pyroxene. So therefore, some water will have to come out, or some CO2 will have to come out. And because it's a closed reaction, there is nothing going out or into the environment. So it happens in closed situation. So therefore, the water or the CO2 which comes out of the minerals are going to stay around, and actually by being around it in a closed environment, the pressure is going to build up, and finally when it built up too high, then it actually breaks up the rocks around the metamorphic area, and it will cause changes in the surrounding rocks. These changes we call metasomatism. So the metasomatism are the changes in the surrounding rocks caused by this highly pressurized fluids and gases, basically. It's called metasomatism, or the chemical activity during metamorphism. Okay, the next thing we got to talk about is the pressure, the texture of the metamorphic rocks. And I already mentioned the most important thing is because of the dynamic or directed pressure, which is coming from one direction, and the minerals are going to behave like when you hit the first domino, they all flatten out. The rocks are actually going to flatten out, and we call this foliation. This foliated texture is very characteristic for the metamorphic rocks, but you cannot mix it with the layers of the sedimentary rocks. It's very thin layer looking, but as I said, it's foliation, it's not layer. Many times you can see the original sedimentary layers and then the foliation, which is the metamorphic process. So the texture is when you have dynamic pressure, it will be foliated texture, okay, foliated. And the other kind I want you to know is the non-foliated texture, which we also call crystalline. And when you see a rock which has this non-foliated crystalline texture, you will kind of see it's like sucroic, when you look at sugar, that's how it looks like. You can see the crystals basically, and you feel like you can look into these crystals. The third thing you have to know about is the so-called porphyroblasts. Porphyroblasts are minerals which during the high pressure temperature environment, actually they love growing. They love the high pressure temperature like some of us do. And they just grow big and push everything else apart. One of the very characteristic one is the garnet. See, like there is a core in New York with this extremely big, sometimes gem quality garnet. So they do mine these rocks for the gem quality garnet. See, this is a beautiful little heart garnet. Isn't that pretty? Anyhow, the other really common minerals which will make porphyroblast is the staurolite. The staurolite is a silicate mineral, and it's kind of famous because around here we have this fairy stone state park. Fairy, like the fairies. It might not be. I might not spell it right. I'm sorry if I don't. The fairy is the, we have not far away at Bassett, we have the so-called Fairy Stone State Park, and there is a legend there. Like if you look down in the soil, you will find these little staurolite crystals. Most of them will have this angle, the 65 degree, like this is about 65 or 60 degree. Basically what we have here, this staurolite crystals, which are silicate minerals, will do twinning. Twinning is just like with humans. When the twins grow together, they actually Siamese twins, because they will have penetrating twinning, like one crystal penetrates through the other one. And we have different twinning rules. The most common is the 65-degree angle, but there are some cases when actually they are 90-degree, and then they look just like little crosses. So somebody who first saw these staurolite crystals uh, with the perfect 90-degree angles reminded them to little crosses. So therefore, they come up with the legend that when Jesus Christ died, the angels were crying and their little tears become little crosses in the ground. So people go out and collect those little crosses, which the case is that you have to pick up about 15 to 20 60-degree twins before you find one 90-degree twin. So that is relatively rare, the 90-degree one. But it's kind of cool to go out there to Firestone State Park and hunt for 90-degree starlight twins. So if you ever go that way, usually there is a little location. It's like a little gas station, and you can go up in the woods and dig a little. You're not supposed to have any tools, but if you have like a little screwdriver or something in your pocket or somewhere, it's okay, I guess. And you can just dig. You dig half an hour, for sure you'll find like two 90-degree staurolite. That's kind of interesting. The next thing you will have to know is the classification of metamorphic rocks. And I guess I'm going to stop this segment right here, and we'll start the second one on the metamorphic rocks. So I will see you later.